Okay, today we're going to learn how to solve initial value problems, differential equations using Green's function. So let's start with an example. Here is an example. You have a differential equation here. It's a second order non-homogeneous differential equation, and you have some initial conditions here. It's called an initial value problem because it's got initial conditions. The first thing we'll do is break this problem up into two problems. This problem and this problem. Notice in this problem you have the same problem, except the sign has turned into a zero. So this makes it a homogeneous differential equation. So you have the same initial conditions, but the differential equation has turned into a homogeneous. So that's one problem we're going to break this up to. The other one is here where the sign has remained, but the initial conditions have turned into homogeneous initial conditions. In other words, we have the values of 0 instead of 1 and -1. So here the differential equation became homogeneous. Here the initial conditions became homogeneous, equal to 0. The differential equation is equal to 0, or the initial conditions are equal to 0. Okay. So to start off we'll start off by solving this differential equation. This is a homogeneous second order differential equation. We've already solved this, except I haven't solved the initial conditions for you in previous differential equation lectures that I've given. So we'll solve for this, turning again r squared and r to the 0 because there's 0 derivatives. 2 derivatives is r squared. 0 derivatives is just simply r to the 0, which is 1. And we have this, and the solution to this algebraically is r equals plus or minus I. And we've already discussed this, that when you have r equals plus or minus I, of course, you have a cosine of 1t because the number here is 1. So the 1 goes in here, and a 1 goes in here. The real part 0 is the e to the 0t. I've discussed this before in other lectures, so I'll refer to the other lectures rather than wasting your time here. What we'll do next is use the initial condition t equals 0, y equals 1 here. And we'll plug it into this equation. So if you put a 1 in the y, there's the 1. Put a 0 in here and a 0 in here. Cosine of 0 is 1, so you get a, and sine of 0 is 0, so you'll get 0. So here we'll get a equals 0 when we plug in this initial condition. We'll take the derivative of this. The derivative of y is y prime. And the derivative of cosine, of course, is negative sine, and the derivative of sine is cosine. So since this is negative sine, when you stick in a 0 into the negative sine function, you'll get a 0 here. And this will become, the derivative will be cosine. When you stick a 0 into the cosine, the derivative, you'll get 1. And so we'll get a 1 times b, 0 over here. So b equals whoever y prime is, and y prime is -1. So there's the -1. So we'll get b equals -1. So now we know a and we know b. Once we know a and b, we know this homogeneous solution. A will be 1 and b will be -1. And I've written that right here. So this is the solution to this equation. We now need to solve this equation, and once we solve both of these, we'll have the solution to this problem over here. Okay, so let's try to solve this differential equation here. The way we're going to solve this, this we've done before, but the way we're going to solve this is we're going to use Green's functions. Now, what you have to do is you have to find a table of we're not going to derive the Green's function. That would take too long. So we're going to use a table of one-sided Green's functions. And we need to look up the Green's function kind of like we would with a Laplace. We'll look at a table of Laplace transforms, which I've discussed in lectures before. So in the same way, there's tables of Green's functions for specific roots or homogeneous differential equations. And for this homogeneous differential equation, or this root, the Green's function for this differential equation here is 1 over b, the sine of b, t minus tau, and parentheses there. So we find this in a table of one-sided Green's functions. You'll have to look that up on Google and find a table, and you'll see that for this differential equation, or these roots, this will be the Green's function. So I've written that right here. For r equals plus or minus I, we get this as our GF, Green's function, for this particular differential equation from a table of one-sided Green's function. Once that we have that, we have this general formula to find something called the particular solution using a Green's function, and that's just simply the integral from 0 to t of the Green's function times the function, which is actually the non-homogeneous part of the differential equation. It will be the sine of t. So the function as a function of tau, and then d tau. So let's use this formula with our example and see who everybody is. Do you know yp? No, we don't know yp. Do you know the Green's function for this differential equation? Yeah, we looked it up in a table. The Green's function was 1 over b sine b t minus tau. And I'm sorry, by the way, the b, of course, was 1 because the number in front of the I is a 1. So we stick in a 1 over 1, that's 1 over 1. And sine of b is 1. We put a 1 there, and so that's our Green's function for this problem. This is the Green's function for any general problem that has this as the roots of the differential equation. So do you know the Green's function? Yep, it's right here. It's a sine of t minus tau. Do you know the function of the differential equation that was given to you on this side? Provided that, of course, the coefficient here is 1. And 1 on the bottom, of course, then this will be the function f right here. So here's the function is sine of t. Of course, we'll change that to sine of tau, the integration variable. So there's our function, and there's our d tau. Can you do this integral? I'm not going to do that integral because that would take up another 30 minutes. So I'll let you go and do this integral. I'll give you a clue. You do want to use trigonometric identity on this sine function, distribute that out, and it's a little bit of a messy integral. But once you do this integral, you will get this solution right here. And this will be your y particular. Why did we do all of that work? Well, once we have y particular, our question now is we've solved this differential equation and this differential equation, and those two are represent this original differential equation, and we'll get y homogeneous is equal y general is equal to y homogeneous plus y particular. So here's y general is the solution here plus the solution here. So the solution here is 1 cosine t minus sine t plus the solution to this is this. So the solution to this is the solution to this differential equation plus the solution to this differential equation. Okay, I hope this was a shorter lecture. I hope you enjoyed this lecture. I look forward to any comments you have at the bottom of this video. Thank you. Bye.